Okay, I think we'll get started. So today we're going to talk about the mole. And the mole is simply a count, much like a dozen. So we saw earlier that the SI unit for amount is the mole. The donut maker's unit for amount would be probably a dozen. So a mole is a lot like a dozen. And so there's a direct amount. For a dozen, for example, that means 12, a count of 12. For a mole, it means a count of a lot more than 12, 6.02 times 10 to the 23 things. So a mole of oxygen would have 6.02 times 10 to the 23 oxygen molecules. A mole of chemistry books would have 6.02 times 10 to the 23 chemistry books. All right, so the mole gives us, it was defined in such a way that it gives us a conversion from grams to AMU. And this is nice because when we look at a single element or a molecule or atom, let's just say atom for now. If we take a single atom, and if we had a mole of it, the amount of grams we would have would be numerically equal to the AMU for that single atom. So for example, if we go, well, actually, okay, let's go to the periodic table and we'll grab a mole of sodium. Now, remember, there's an additional thing going on here. In the lab, there's no way we could pull out a mole of a single isotope. So what we're getting is the weighted average, isotopically weighted average of the mass for sodium here on Earth. So it's the Earth's percentage. So this is a number straight off the periodic table. And so we have 1 mole of sodium, we have this many grams. If we have 1 mole of chloride, we have this many grams. Chloride's a heavier atom. So a single atom of chloride is heavier than a single atom of sodium. Now, when we make a compound such as sodium chloride, then we simply add the masses to get the what's called formula weight or formula mass, sometimes called molecular mass, even if we aren't talking specifically about what's technically a molecule, or compound mass. And so that's what we see here. So this has a formula weight or formula mass of 58.44 grams for every 1 mole. So the fundamental building blocks of calculation now is going back and forth between grams and moles and moles and grams. So that's going to be the early stuff in the homework and the early part of this course. One thing you've got to get down is this ability to calculate grams to moles and moles to grams. So let's look at an example here. Let's say we have 100 grams. So we've got 100 grams of sodium chloride. Now we can set up, these problems lend themselves really well to this unit analysis technique. So we set up in kind of a grid here, 100 grams, and then we use this as a conversion factor, basically. So 1 mole of sodium chloride is 58.4 grams, as we saw up here. So now we've got grams of sodium chloride on the top and on the bottom, and so those will cancel. And if we look at what's left, we have moles of sodium chloride. So this unit analysis technique, which we won't be able to use all the time, some of the more physicsy problems, it gets in the way, but a lot of the more chemistry type problems, this is a very valuable technique, and you should learn to use this methodology. And your general chemistry book, whichever one you have, will definitely use this. So we're left with moles of sodium chloride, and we just simply multiply that out. So 100 times 1 over 58.44, and we get 1.7 moles of sodium chloride. Now we want to be able to go the other way. Say we're given a certain amount of moles. So here we're given 3.5 moles of sodium chloride. Now we put this ratio the other way. We want the moles of sodium chloride to cancel and then leave us with grams of sodium chloride. And so we multiply this out, 3.5 times 58.44, and we get 205 grams of sodium chloride. So the homework has a lot of practice on this, and you want to get this down really, really well. So it just takes a few times. I think you'll pick it up pretty quickly. Now let's look at a little bit more intricate problem, a couple of them. So first we'll talk about percent composition. So here what we're trying to do is figure out, given a compound, what percent is each element. So let's say we want to do this for carbon dioxide. So 1 mole of carbon dioxide is 44.1 grams. That comes from adding up the mass from carbon off the periodic table and the mass from oxygen off the periodic table times 2. And so we get about 12 plus about 32, that's 44. And that's where our grams come from. Now, percent of carbon, there's 1 carbon in the formula. Carbon is 12. So we put the mass of carbon over the total mass of the compound, multiply by 100%. We see that the mass component of carbon dioxide is 27.3% carbon. Likewise, for oxygen, we have 2 now oxygen atoms in this molecule. Each one is 16 times 2. There's our 32 divided by 44 times 100%, and that's 72.7. So of the mass of any given sample of carbon dioxide, 27% is going to be carbon, 72% is going to be, or 73% is going to be oxygen. Okay? So these are determining the percent composition. A little bit more difficult, but still pretty straightforward, is determining what's called the empirical formula. Now, the empirical formula isn't the chemical formula. It can sometimes be the chemical formula, but what it is it's the ratio, it's the molar ratio of the atoms in a compound. We're going to do this just for 2 different atoms, but this could be for any number of atoms. Elements. So let's say we've got a 100-gram sample of carbon dioxide. Let's just pretend we don't know the formula for carbon dioxide, even though it's given to us there in the name. And we send this off for analysis, and elemental analysis tells us that the only elements we have present in our sample are carbon and oxygen. So we don't have any nitrogen, we don't have actually any hydrogen. So this is what the elemental analysis comes back from the lab. And then it says in this sample, 27 grams are carbon and 73 grams are oxygen. Okay. So what do? Well, we'll take the 27 grams and then we want to figure out how many moles of carbon that is. Remember, we're pretending we don't know the formula for carbon dioxide. So 1 mole of carbon, 12 grams. So this will cancel the grams, and this gives us 2.73 moles of carbon. Now we do this same thing for oxygen, 72.7 grams. Grams of oxygen cancel. And so we have 4.54 moles of oxygen. So then we look at the ratio. We want moles of carbon over moles of oxygen. So we put the numbers we calculated and we figure out what that is. And it's about 1/2. Now these should be low fractions. So if you're getting, say, like 0.667, well, that's 2/3, right? So you might not get precisely a low fraction. So let's say this had come out, I don't know what this would come out to, but let's say it came out to 0.49. Well, we'd say, well, okay, there's some error in there. We're expecting a low fraction, so that's probably 1/2, right? Not 49/100ths. So this suggests to us that the mole ratio in this compound is 2 oxygens for every carbon. So the empirical formula is CO2. Now that does not tell us what the formula is for carbon dioxide. And again, if we're pretending we don't know this, we would need an additional piece of information, like total number of moles or something like that. And but right now what we can get is the mole ratio. So this means that whatever the sample is, it's either this directly, the chemical formula, or it's some of these ratios. So C2O4, C3O6. Now, of course, we know it happens to be this, but this analysis would limit us to these choices. Let's take another example. A molecule that's really important to all physical chemists is benzene. It's a molecule that's used a lot in just testing different new methods and that sort of thing. It interacts well with light, so it gives a good, it's a good useful molecule. And then it's very important in organic chemistry. So benzene, something we should know. C6H6. Well, if we had done this kind of analysis on this, we would have gotten an empirical formula of 1 to 1. 1 mole to 1 mole of carbon to hydrogen. And thus, we wouldn't have gotten the C6H6, but we see that we would get that same ratio. So the empirical formula of benzene is CH, and the chemical formula is C6H6. So C6H6 is benzene. CH is not benzene, but that's its empirical formula. All right, so that's it for the mole. A critical concept, and sometimes it's funny how this, you look at this, oh, this should be super, super easy. Mole is just like a dozen, and I'm used to that. But it does take a little bit of work, so go ahead and put a lot of time in here on these homework problems. Look at your book and try to make sure that you can very quickly go from grams to moles, moles to grams, and use them in these types of calculations.